Hello everyone, my name is Hossein. In this series of lecture, we are going to study Control System 2. Control System 2 is essentially about linear control. That is the theory and method for designing controller for linear system in the state space framework. In this lecture, we will highlight several key control concepts. Along the way, we'll see how linear control provides both the foundations for nonlinear control and practical tools for controlling many nonlinear systems. This course helps us analyze and design controller for models that obey the superposition principle. Control system has an input. This input could be a vector. It could also have an output. This output also could be a vector. In this course, we show vectors in boldface. This figure shows the response of a system to two inputs, where one input is twice the other. As observed, when the input is doubled, the response is also doubled. This demonstrates that the system obeys the principle of superposition and therefore is linear. You already know how to model a system in your field. In practice, most systems are nonlinear. Also, you don't need to be an engineer. Go back to your real life experience. Is every system you work with linear? For example, when you push the throttle twice, does your speed become twice as large? I think that's not correct, right? It depends on many things. Your current speed, the gear position, and so many other parameters. So, we can say that the perfect linearity for all inputs is not realistic. But the main question here is, why study linear control when real systems are nonlinear? The answer is that not only does linear theory help us have a deep understanding of nonlinear systems, but also linear control is an efficient approach based on a very strong mathematical background that can control nonlinear systems. Today, throughout this lecture, I want to briefly introduce the intuition behind linear control and make a connection between nonlinear systems and linear system theory, and explain why linear system theory is important for the control of nonlinear system, and from a practical perspective, how we can use linear control to control nonlinear system. To answer these important questions, I will first review some fundamental concepts. The first concept is state space fundamentals. In this part, I will show how we model a system as a nonlinear state space system. I will define the state space and introduce the idea of trajectory and equilibrium point. In the second part, we will discuss the control problem in state space. We will see that most control problems can be separated into two control categories: trajectory tracking and regulation around an equilibrium point. After that, we will move to the stability of trajectories. Here, we will define two types of stability: Lyapunov stability and asymptotic stability. We will analyze the behavior of a system near a desired trajectory. In this part, we will derive the perturbation state equations and see how they govern the dynamic of a nonlinear system near a trajectory. This perturbation equation consists of two parts: a linear part and a higher order part with respect to the perturbation states. Once we have these foundations, we will explore the intuition behind the linear control theory, why it works, and how it can be applied for nonlinear system. Finally, we will discuss the concept of linearization of nonlinear system and summarize the steps for designing a controller for a nonlinear system using linear control theory. At the end, I will show a flowchart of this design process. Keep in mind that this flowchart is not yet complete. We will expand it with other design block in future. Now, I want to discuss about concept of state space. Assume you have a system model in your field. For example, you are a power system engineer and you model a power system with a mathematical model. And as we know, it's a kind of nonlinear system. During this discourse, we will represent systems in a state space form. Therefore, it's very important that you know the foundations of a state space and how to define your model in state space. Before we define the state space, we should define a state variable. The state variable is the minimal set of variables whose values at a given time together with the input for future times determine the system's future behavior. It's very important to pay attention to the word minimal. Yes, you can describe your system with many variables, but the state variables are the minimum set we need to define the whole behavior of the system. When we discuss the realization of the system, we will talk about this minimal set more. Now we can define state space. If the number of state variable is n, we can define an n-dimensional state space and whose coordinate axes are x1 axis to xn axis. Here, each coordinates correspond to one of the state variables. This vector space is called the state space. Any state can be represented by a point in the state space. Next, an important thing in the control theory, especially model-based control theory, where we assume we have a mathematical model of our system, is the state space equations. In state space analysis, we are concerned with three types of variables involved in the modeling the dynamics: input variables, output variables, and state variables. Okay, we assume we have our inputs, m outputs, and n states. When we discuss dynamics, we discuss the evolution of the system. This evolution is related to the derivatives of the state variables. Then, as you can see, in the state space, we have first order differential equation of each state as state equations. For example, x1 is equal f1, and f1 is a function of x1 to xn, u1 to ur, and t. Yeah. Sometimes our state equations are a function of t. The presentation of this evolution in state space is a state trajectory. We can display it in our n-dimensional space. where the arrow direction indicate the progress of time. But not all the state variables are always important to us. Because of this, we should define output variables. Output variables are the variables that we want to consider and focus on. These variables sometimes comes from our sensors, and sometimes they are quantities we want to control or track them. The output variables can be different from the state variables. However, because we define the states as a minimal set that together with the input determine the future behavior, and because the output is one part of the behavior of our system, the output variables should be a function of the state and inputs. And it also, like state equations, it could be a function of time. For example, our first output variable can be written as a y1 equal g1 of x1 to xn, u1 to ur, and t. And similarly for the other output variables. Now we can concatenate all these variables and write the state and output equation in vector form. If we collect the entire set of states into a state vector, the outputs into an output vector, and the controls into a control vector, then we obtain the vector form of the state space equations. I want to lead you out of the abstract world of equation and review these concepts together with an example. We have the well-known system of spring, damper, and mass. From basic physics course, you know that the model of this system is a second-order differential equation. If you know how to derive this model, that's great. If you don't know, no problem. Just accept this as the model of the system. In this equation, K and B are spring and damper coefficient. M is the mass and U of t is the excitation force or the input of the system. More realistically, the spring and damper coefficient are not constant. They are function of the amount of compression or extension they experience. Here we have a load cell. It's a kind of sensor that is placed between the mass and the spring. The load cell measures the force at this location. Now we define this model in a state space. Here we have just one second order differential equation, so we should have two states. We assume the first state is the position of mass. Here it's x, and the second state is the speed of the mass, x dot. So x1t is equal x dot t is equal x2, and x dot 2 is equal x double dot. So the state equation for the first state is x dot 1 equal x2, and the state equation for the second state comes from the mass spring damper equation. If we substitute x double dot equal x dot 2, x dot equal x2, and x equal x1, we obtain the second state space equation, the second state equation. The output equation here is the measurement of the load cell. That is the force that a spring apply to the mass. As you can see, the output is the measurement of a sensor in our system. We summarize our example as follows. We define the state vector as a position and velocity of the mass. Concatenating these two variables give our state vector. The excitation force is the input, and the load cell measurement is the output. Based on these three elements of the state space, we write the state equation and output equation for the system. Most control tasks can be divided into some tracking control problem. In a tracking problem, you have a time-varying reference signal RT. You want to design the control input so that output follow reference signal. For example, here, this is R of t, and you want your output yt follow this reference signal RT. This is y of t. You want to design the control such that y of t track R of t. We can define the tracking error E of t equal reference signal minus output. When the error signal goes to 0, there exists a nominal output, we call that y bar, such that y bar equal R of t. And also there exists a nominal state x bar and output u bar satisfy output equation. The corresponding nominal state x bar and u bar are not generally unique. Several pairs may produce the same y bar. We are not discuss how to design nominal state and input in this course. This is the subject of trajectory design, and it's a complete course in each field of engineering. We only assume in this course we have the result of trajectory design. Given any such pairs, substituting these into the state equation yield x dot equal x dot bar equal f of x bar and u bar. Thus, every tracking problem corresponds to some trajectory in a state space. A special case of tracking problem is the regulation problem. If the desired signal RT is fixed or time invariant, then the tracking problem is called regulation. In this case, when E of t is equal 0, the nominal output is time invariant, and there exists time invariant state and input. We call this x star and u star that satisfy the output equation. Because x star is fixed, its derivative also must be 0. So x star is equal 0. This implies the state equation evaluates to 0 at x bar and u bar. In this sense, a regulation problem corresponds to maintaining a point in the state space. Formally, We call this point in a state space as an equilibrium point. For a system x dot equal f of x and u and y equal g of x and u, a state x star is an equilibrium point under the input u star if when the input is held constant at u of t is equal u star and the initial state is x0 is equal x star, the state remain there for all time. In a regulation control problem, the goal is to design a controller that keeps the system's state close to an equilibrium point associated with the desired constant output. So far, we have concluded that a tracking problem is equivalent to following a trajectory in a state space. Now it's time to define the stability of a trajectory. Let x bar be our desired trajectory of the state space. We say this trajectory is stable or Lyapunov stable if any other trajectory x prime starting from a point in a neighbor of x bar doesn't drift arbitrarily far away from it. In this figure, the surface perpendicular to the time axis represents the state space. You can see that x prime t starting at t0 within a small radius delta around x bar stay within an epsilon neighborhood of x bar as time evolve. If every trajectory that start in epsilon neighbor of x bar or stay within an epsilon neighbor of x bar, then we called x bar as a stable trajectory. As we have seen in the definition of trajectory stability, there is no guarantee that that starting near our desired trajectory will lead us to converge to it. The trajectory may remain close, but not necessarily approach the desired trajectory. For this reason, we introduce the concept of asymptotic stability. A trajectory is asymptotically stable if whenever another trajectory starts within some neighbor, say within a radius b of the desired trajectory, it's not only stay close but also gradually converge to the desired trajectory as time goes on. For example, in this figure, you can see the trajectory x prime, which begins within the b neighbor of x bar, gradually converging to the desired trajectory over the time. If every other trajectory that started from b neighbor of x bar converge to x bar gradually, then we called x bar as a asymptotically stable trajectory. In order to determine the stability of a trajectory x bar, we must study the nature of trajectories that start near x bar. Suppose we are on a trajectory x of t that is close to the nominal one. So we can write x of t equal x bar plus delta x. And similarly, we can divide or control into two signals, u bar and delta u of t. Here, delta x and delta u are perturbation from the nominal state and input. Now, x bar is asymptotically stable if for any initial perturbation delta x 0 with the norm of delta x 0 less than b, the perturbation goes to 0 as time increase. And also when delta x of t is equal 0, delta u of t is equal 0. We need this second constraint because we want when x equal x bar, u is equal u bar. Because under this condition, our desired or output follow the reference signal. To analyze this, we substitute x equal x bar plus delta and u equal u bar plus delta into the state equation. If expanding f of x bar plus delta x and u bar plus delta u with a Taylor series, we obtain this equation that contains an infinite series of derivative of f of x. And we can express that long equation in a more compact form as follows. Here, a of t is the Jacobian of f with respect to x, its first derivative of f with respect to x. And b of t is the Jacobian of f with respect to u. O of t is the high order term. The high order term are function of order of delta x and delta u greater than 2. After cancelling the common terms, we obtain the perturbation equation which describe how the system behave near trajectory. This equation depends only on the perturbation variable delta x and delta u. It has two parts, a linear in terms of perturbation and a remain consisting of high order terms. The high order term is an infinite series. The linear term generally gives us as a time varying linear system. But in the special case where the desired trajectory is an equilibrium point and the nominal input is the corresponding equilibrium input, the linear term become a time varying linear system. Finally, as the perturbation is equal 0, that is delta x and delta u are equal 0, the high order term is equal 0. But there is no guarantee as perturbation become small, the high order terms goes to infinite, goes to 0, because it's an infinite series and it could be diverge as delta x and delta u goes to 0. Now it's time to discuss the fantastic intuition behind linear control theory and explain why it works even when dealing with a nonlinear system. So far, we have seen that around a desired trajectory x bar and u bar, the perturbation equation contains two parts, a linear and a high order term. The high order term is an infinite series. Keep in your mind, it's an infinite series. Suppose we choose a feedback. For example, u is equal minus k of t delta x of t. With this feedback, we link the input and the state throughout a linear relation. Then, when delta x is equal 0, uf equals 0. With this relation, we could satisfy one of the constraints of our stability. Substituting this into the perturbation equation gives us a closed loop local model, which now depend entirely on delta x. If we ignore the high order term and keep only the linear term and use delta x prime for linear term, we can design k of t so that the closed loop perturbation delta x prime of t goes to 0 as t goes to infinite. But here comes the key question. If the linearized perturbation delta x prime of t converges to 0, does this imply that actual nonlinear perturbation delta x of t also converges to 0? It means if this part gradually comes to 0, is there any guarantee that the high order term that is an infinite series doesn't diverge? If we answer this question, we can answer what's the intuition behind the linear control theory. I want to answer this question using important result from nonlinear dynamical system theory. The key question is, when does a linear design actually guarantee, or when does the linear stability, because why I said stability, because we say the linear part converges to 0 regardless of any initial condition, then it's a kind of definition of asymptotic stability of this linear system. Now, the key question is, when does a linear design or a linear stability actually guarantee a stability of a nonlinear system? To answer this, I draw on result from nonlinear dynamical system. I don't want to dive into the full theorem here, but I highlight the condition under which convergence in the linearized model imply stability of the nonlinear system. It's obvious if our linear system diverges to infinite, our nonlinear system is not stable. We can consider two cases. Suppose our nominal trajectory is an equilibrium point. In this case, A and B are constant. We discussed about this before. Nonlinear system theory tells us that if the perturbation in the linearized system delta x prime of t converges to 0, regardless of its initial condition, or if we can find b, that when delta x prime of t is less than b, delta x prime of when delta x prime 0 is less than b, the delta x prime goes to 0 or converges to 0, then the actual nonlinear perturbation delta x of t also converges to 0. It means the high order term is converged to zero, or it means the high order term that is a infinite series doesn't diverge. So this means the nonlinear closed loop system is locally asymptotically stable near equilibrium point, or it's locally asymptotically stable. We called locally because we explore our system near equilibrium point, and every conclusion are valid near that equilibrium point. This is a powerful result. It allows us to design the controller for nonlinear system by linear system around an equilibrium point. We can be confident that within some neighborhood of the equilibrium point, the linear system will also be stable. So the controller can regulate the state to the equilibrium point. Now, suppose the nominal trajectory is not equilibrium point. It's a time varying trajectory. In this case, A of t and B of t are time varying. Here, if the linearized perturbation delta x prime of t converges to zero, it doesn't always imply that the actual nonlinear perturbation delta x of t is also converged to zero. It means there is no guarantee that our high order terms or that infinite series converge. It could diverge. However, if the convergence of the linearized system is fast enough, especially if it decays to zero at an exponential rate, then the nonlinear closed loop system is locally asymptotically stable near the trajectory. Formally, this means that there exists some alpha greater than zero that the norm of delta x prime is proportional to an exponential function. Okay, let's review what established so far. We started from a nonlinear tracking problem, and we showed that the nonlinear tracking problem can be recast as a linear regulation problem. It's a very important result. We show that a nonlinear tracking can convert to a linear regulation problem. Why I say regulation? Because here we want our linear system stay near zero or converge to zero. And if you remember, when we defined regulation problem, we said regulation problem is a tracking problem that our reference signal is a point. Here, our reference signal in a linear system is a point. That point is zero. Okay, now I want to define the linearization. Linearization is the process of studying a nonlinear system around the desired trajectory by deriving the perturbation equation and then eliminating the high order term. What we have done until now. We can also linearize the output equation and obtain the perturb output equation, and these two together give us linear perturbation state space model. Until now, we conclude we can convert every nonlinear tracking problem to a linear regulation problem. Then we can easily design our system based on linear control theory and use that for nonlinear system. Now I want to summarize design of a control for a nonlinear system. We first have a nonlinear system model. Then we can drive equilibrium point or design or desired trajectory, and then linearize the system around desired trajectory and drive A of t, B of t, C of t, and D of t, and then design controller using linear control theory and apply the controller to the nonlinear system. That's it. It's the intuition behind linear control theory. Thank you.